In a previous video we mentioned that VSEPR wasn't saying a thing about orbitals. And that's kind of strange since we've really seen that electrons can't be localized in space. We have to think of them as being areas of probability where we're likely to find an electron. Well, Linus Pauling was one of the famous names out of the last century in chemistry, and he basically founded, not solo, but he was largely responsible for the founding of the idea of quantum chemistry. And he won a Nobel Prize in, I believe, 1954 for his work that we're about to summarize here. He theorized that our valence electrons in those atomic orbitals are going to be different once you're in a bonded atom. In other words, when you have an atom by itself in space, those orbitals change once it becomes close enough to another atom that it starts to interact. And that interaction itself is called the bond. In other words, the orbitals in our molecules are going to be different than, but still made from, atomic orbitals. The electron started out in some region of space, and then it started interacting with another area of space that it could be in. Now, the number of orbitals that we put in are still going to have to give us the same number of orbitals coming out. And that's because we're still going to only have 2 electrons occupying the same area. Because they have different quantum numbers. All their quantum numbers are the same except for ms. The spin of one will be up and the spin of the other will be down. So they're allowed to be in the same space. The orbital will still contain 2 electrons. And this is going to be the core of our valence orbital theory. Now let's just see exactly what happens when those come close together. Now, I'm omitting the s orbital in these 2 sketches, just because that would be a real mess to see. In fact, I'll go ahead and sketch it on here for a second. Remember, our s orbital would be about the same size as the p orbital, coming out here as a sphere. And you can see that that's going to be a little bit messy. So for the moment, let's just assume there are 2 more electrons that we aren't currently showing, an upspin and a downspin, and they're in that s orbital. Now suppose that these fluorines come close together. Now keep in mind, one of those orbitals won't be totally full because there's only 7 valence electrons. If these 2 electrons are being shared, they're going to be in this region of space that's going to overlap as these come together. There's going to be an advantage energetically to having them both in the same region of space. That's why they're going to form an orbital together. Once they do that, we're going to have a region of space where there's a good likelihood of finding 2 electrons, which is also called an orbital. Since it's spending all its time in the central area, this outside area is going to shrink down dramatically. It's still going to exist. We're usually not going to draw it in our sketches, but there's still going to be a chance that the electron loops around to the other side of each of the 2 nuclei. The thing is, with that electron density being right here, those other 3 orbitals, the s and the 2 p orbitals that remain, are going to be shoved further away. They're not going to spend much time on this side. They're going to spend more of their time on the opposite side. So we're going to have our orbitals over here still with an upspin and a downspin. And same thing over on this atom. And they're going to be spread out in space. So by making this single bond in the middle, these end up spreading out. And this is looking more and more like what we're used to seeing from VSEPR theory in terms of the structure.